Hello everyone, I am Jyoti Divedi and I am from MTech AI. As a part of my course Foundation Models and Generative AI, today I am going to show you my research paper which is based on code graph model. This is basically a graph integrated LLM for repository level software engineering task. Let's deep dive into it and see what it actually is. The main motivation behind this research paper is that the LLMs, we all know, are great at code level tasks. But in real life, and especially software engineering domain, everything is basically repositories. And LLMs don't do quite good when it comes to repository. So the first main motivation is very clear that real world software engineering being the large scale systems are basically repositories, and LLMs like Llama or even Quen shine at single functions but not at full projects. They miss the wiring between files, leading to 20 to 30% success on benchmark like SWE bench or even agent based system like SWE agent. They are powerful but unpredictable and often closed source. Our main aim is to have an open source agentless model that reasons over entire repository like a map, and that too for the LLM brains. So this is how we got the motivation for this paper, and let's see ahead. Now, what is the core motivation and innovation that we did in this paper is we basically thought of feeding LLMs with repository structure, and that too from a code graph. Now, what is a code graph is a side by question, like we will deal with it in the subsequent slides, but for now just understand that we deal with this problem using a code graph. In code graph, we have nodes for files and functions, edges for dependencies. I'll introduce CGM. This CGM integrates graph semantics and structure directly into the LLM brain. Then it pairs with a RAG, which is basically a pipeline having rewriter, retriever, re-ranker as well as reader. And what is the work of basically rewriter? So rewriter basically gives us better queries. Retriever builds the subgraphs, re-ranker picks the files related to it, basically key files, and the reader generates patches. There are just these four rack pipeline based agents and four steps. And in this way, we have done the solution. Let's see forward what it is. This code graph model works on code LLMs like Llama, Quen, DeepSeek for generation. It uses graph-based models for structures. It uses agent systems like SWE agent for software engineering tasks and agentless RAG for retrieval. But the problem is none fully integrate graphs into LLMs, and that's where CGM shine. It basically helps with all these stuffs, flattening the close gap without any complexity. Now let's see what is a code graph. So code graph has following graph elements like nodes and edges. What can be nodes? Nodes are basically the repository, package, file, class, functions, etc. Edges can be hierarchical or reference. Hierarchical edges basically means parent to child relationship, and for reference it basically means any calls or imports that we do in the repository. These attributes are basically code tag, text and metadata. So you can see this simple graph that I have made here. Here we have a repository. It is connected to packages and then files. So basically this is basically a code graph. Now see how the graphs are basically plugged into the LLMs. We have following layers: a semantic layer, a structural layer, and then it follows by training. At semantic layer, we basically chunk the node text, encode it with code T5 for codes and comments, and then a two-layer MLP adapter, which helps us to get it to LLM space. Then we compress it to tokens and for getting better context stretch. And then we have structural integration. In structural integration, we basically try to mask several parts of the graph to have causal attention, like where the neighbors only talk, and basically it is like how we implement graph neural networks into LLMs, like passing of graph neural network into LLMs. Basically this stuff is also the same like that. In training, we use LoRa fine tuning for lightweight based, and we have subgraph reconstructions as a pre-training, and then noisy fine tuning too on SWE pairs. This is how basically the architecture works. Our CGM is a four-step pipeline, as I said earlier. It starts with the rewriter. Rewriter has basically two components, extractor and inferer. What's the work of extractor is that extractor extracts the prominent or important keywords and files from the query. It gives those keywords to the inferer, and it enriches it with functional descriptions. Like it basically gives it proper descriptions, like details for better research and search, I mean better search. And all this is basically powered by Quen 2.5 prompts, and it actually enriches the query that we usually give. Now retriever does lexical match for exact anchors like string search that we do on keywords, and then we have semantic search for CG large, like fuzzy kind of things, and then we expand it to like one hop expansion, one like basically we do one hop to the neighbors, and then the root or the repository for context including full file internals. Basically the output after this entire retriever is a subgraph with all the file internals that are needed for our code or basically our repository. This avoids flat rags noise and focuses on relevant wires between all the files that are present in the repository. You can see there is a graph. We have selected subgraphs, extracted nodes, as well as inferer nodes. From retriever subgraph, we basically, I mean re-ranker basically scores top 10 to top 5 files by query relevance, and it uses file skeletons for that. So basically it does file ranking, filtering references from targets. Then comes the reader. Reader basically takes subgraph tokens and that full top 5 files from the uh, re-ranker. It generates patch based with global structure, local details, basically ensures unit test passing via semantic or structure leverage. And basically the input to this reader is subgraph, re-ranker files, and output is a test passing patch. This closes the loop agentless. If you want, you can see this. I'll just hide my video for a while so you can see. This is the entire structure of reader or basically CGM as well. As discussed earlier, our graph rag basically follows this four-step pipeline where rewriter extracts keywords, enriches the query, retriever finds the anchor nodes, builds the subgraph, re-ranker basically ranks the files, and reader creates the final patch. All this gives us the SOTA performance in just 4 steps, and all of these are basically open source. For evaluation, I evaluated on issue fixing, SWE benchlight, and also verified for Python and SWE bench on Java as well. And we did code completion by cross code eval for cross files and complex code eval for APIs and tests. And metrics used here were a percent R for fixes, EMES for similarity, and regress. It was basically regress with all the unit tests. This was basically the evaluation setup for our CGM. As you can see here in the results, the CGM SWE on Python achieves 43% on SWE Benchlight. This was the best among all the open weight models available. Also on Java, we had around 14%. Basically, we had double the agent there, and on verified also it was like around 50%. So this gives us a very good result for all the result statistics. You can see, I'll just hide my video for a while. These were all the results that we got. When we did for code completion, we got strong EMES score on cross code eval, and especially you can see 50% for Java, and complex code eval was also around 15 to 20% increased in comparison to RAGs and like BM25 and RepoFuse. This basically outperforms Mistral 123B, and subgraphs also preserve deep knowledge, and it is basically better than the text sequences that we usually give to the LLMs. The ablation also confirms that each RAG module basically adds a big value to our results. Like without re-ranker, we had 25%, and with full, we had actually got 34%. Like for the complete view of the table, I will just hide my video so that you can see that without rewriter these are the statistics. And basically we can see that joint tuning is also increased by 5 to 8% in EM. Pre-training basically boosts reconstruction, and so our design basically pays off. Now, let's see the strengths and limitations of this research paper. It is open source, as we all know till now. It is agentless and predictable and has explicit structure for reasoning. But there are some limitations with it. The limitation is the cost that will be incurred for graph building. Also, when it comes to very large repositories, scaling to that high level of repository is a tough task, and fine tuning will be needed. But there are opportunities for these tweaks, and I hope we can do this in the future research as well. Now let's see the final contribution. So CGM basically introduces graph aware LLM, and it enables effective retrieval without agents using RAG and achieves top open source result, as we all discussed till now. Final future work that we can do is efficient graph construction so that the cost incurred will be less, improved retrieval and re-ranking. And with that, we can also explore lighter LLM backbones to have better possibility to use it in the future. Thank you.